So, welcome everybody on this Train the Trainer event for Module 2. So, as you recall, this is the module meant for management of the system of heat sources and storages, which is meant to supply our consumers in historical urban centers. And we are here interested in how this heating system can be made as efficient as possible with smart actions on the hardware that is available on different pilots. So we have 3 pilots which include also heating systems. This is a pilot in Austria, in Weiz, then in Croatia, Bračak, and in Slovenia is Lendava. And they are of different setups. And actually, as you know, we try to adapt the description of the site used for optimization for each of the pilots to make it as relevant as possible for a particular pilot, and it made us significant troubles with computations, optimizations, numerics, but okay, we are fighting with. You will see the results. What we are getting. Still, I am not completely satisfied with how the optimizations run, but you will be able to see already from the results we have now how the tool is going to be used. I will put the stress on what user needs to provide and what it gets back. So the main purpose of this tool would be to advise the users on the site how to run their plant. So it is very interesting dynamic system and very interesting optimization problem, and of course, also challenging, but that's the reason why it is also not easy to figure out for the user, even though he knows or she knows the system very well, even though maybe he is expert for this system, but he is not able to decide in an optimal way when to, for instance, switch certain heat source on, when to switch it off, in order to be able that this system satisfies the predicted heating load for the current day. So we would be actually giving an advice how to switch on and off different heating sources on the site in order to gain optimal cost in operation of the system at the end. So system is dynamic, and for instance, usual, let's say, simple automation available on the site just regulates certain temperatures on different set point values by just using the knowledge of the current temperature and some simple logic. Which, of course, works well, but also is not the most efficient way to go. Especially this holds for the cases when storages have significant volumes, and when the actions we do currently have consequences for a considerable amount of time ahead of us, and it's really not easy to figure out what would be the best to do. So the idea of the module 2 would be that the user enters some predicted heat demands for the site for day ahead, and then to be advised how the system should be run to gain on its optimality. Of course, this can be used, for instance, to to tune the local automation, different timers, when to switch on certain source, when to switch it off, which is usually a decision that is done ad hoc, I would say. And here there is a significant space for increasing efficiency in terms of energy consumption, so primary energy use, but also in terms of money. Okay, so first I would start with actually a try to make the module as general as possible and as relevant as possible for a broad setup of different heating systems. They are very different in nature, indeed, and even for the case of the pilots we are having here in Store4HUC, the pilots in Lendava and in Bračak, I would say, are more exotic heating systems where you have different heating sources available or very special storages which are not so common by now, and they require, let's say, a special attention, and we are giving them a special attention. While, for instance, whites, to whom we also giving a special attention, you will see the more detailed elaboration of Philip. It's Philip R. So we have two Philips, Philip Rukavina and Philip Verbans. Philip Rukavina is Philip R. So Philip will show you about whites more in detail. And then Philip V about the Lendava site. But whites is, for instance, the site which is more common, let's say. So you have just one type of heat source and a usual storage. And for that case, we have tried to make something, let's say, more general. And this is what I would like to show you first, because as you know, Interreg projects should make an impact, should make a broader impact and address stakeholders as much as possible. If we wouldn't have this general approach, then more or less we wouldn't have things to share about Module 2 with general users and stakeholders across Central Europe. And that is why we also decided to create this simplified setup. And I will show you exactly on the parameters from whites how it would operate. And first, I would start with explaining how we consider this general setup. So to make the things as simple as possible, but still relevant for sites, and taking care what are the most usual ways of operation of the site and ways of operation of sources themselves and their constraints. So what we are suggesting, even for instance, for the case when there is a multiple situation of multiple heat sources on a site, even in whites we have actually two. We have two boilers of different powers. We would use like one equivalent source, which would then, after giving an advice how much overall power this source needs to provide, this power would have to be disaggregated on individual sources. But still, the user would be in a possibility to get an advice how to run its system. Philip will give you also more details on this side, how to perform this disaggregation and how to actually evaluate finally the module operation. So don't be afraid, please, of these mathematical equations here. I won't be discussing mathematics at the end. Here they are to provide you the insight. What would be this model we are dealing in this general module 2, which would be for a broader set of stakeholders, for which we would be able to to publish the Excel similarly as for module 1 on the web and engage a broader set of stakeholders with something very interesting and you see also very useful. So we try to model first the temperature in the storage as simple as possible. That's why we would just for this simplified model neglect stratification. But later on in different constraints, we would take them also, we would take this stratification into account. So stratification means that along the vertical profile of the storage, you have actually water of different temperature in the storage. So we would be dealing with some mean temperature of the storage in this simplified setup. The power to the storage is provided from the heat source. The power is sucked from the storage by the heat demand. And we also have modeled losses in the storage, meaning that if you have storage charged for a while because of its environment and let's say not perfect in insulation, finally you will get the storage getting cold if we are talking about the heat storage. So the heat would be dissipated to its environment. So these are these three contributors here that determine how the temperature of the storage behaves. In this simplified general module, the power of the heat storage, which needs to be decided, computed, actually advised to the user for a full day profile. Then we have heat demand that should be predicted and provided by the user. We can discuss it in more detail. What would that mean? But this would have to be provided as an input from the user to get an advice. And we have this third part regarding losses to the environment because of non-perfect isolation. Then next thing is the fact that once you engage the heat source, you don't get it immediately supplying the heat to the storage. It needs some time to warm up. And on the other side, on the other hand, when it switches off, it has some residual heat in it, which can be still used for supplying the storage. And this is what is modeled here with this simple dynamic equation, meaning that this power here, noted with R stands for reference. So this is something that is actually commanded to our heating system. So this is something actually the user would provide to the system, or the automation available on the site gives this information. As I said, sometimes it's, or most usually it's provided ad hoc by certain timers which engage our heating system at a certain time, usually early in the morning, to be able to provide the necessary heat to the storage, such that when the users actually need the heat, it is there for them in the storage already. So this is a simple modeling of some time needed from the time of engagement of the storage finally to provide the heat. So heat up of the heat, once we engage, sorry, not the storage, but the heat source. So heating up of the heat source. And also once it is switched off, there is some residual heating power it can provide. Of course, it is diminishing with time. And finally, after a certain period of time, you cannot suck anything else from this heat storage because it's completely cold. And then the third thing, which is very important, this is this third equation. It models actually that our heat source is differently efficient in its different loading conditions, and you can incur different, let's say, different setups. Sometimes partial load is more efficient. Sometimes full load is more efficient. It depends on the type of the heat source. And actually, this is something that is usually provided in the manuals and data sheets of the heat sources. So this data, how the efficiency of the heat source changes with respect to its power engagement is existing, and it is one of the basic technical parameters for the storage. And in some cases, maybe it's just given like one number and it's considered constant all the time, but usually we have different efficiencies in different points of power engagement, and the model here is created such that we can take this efficiency to be linear with respect to our command, how large the power from the heat source should be. And actually this E on the left-hand side is actually modeling of the primary energy we need to use to run our storage. For instance, for the case of whites, this would be the energy contained in biomass that is used to run our boilers. And of course, finally, this can be converted into money at the end. Usually there is some simple coefficient that provides us a relation between the heat content of the biomass that we are entering in our boilers and the price we need to pay for the biomass. So this would be this simple generalized model, which could be used in different setups. Although it is quite simple, it should be representative for a large group of heating systems, where you might have several different sources supplying the same storage. And if this storage is not exotic, for instance, like the storage in Lendava, then such mathematical setup could be enough to provide the user with the advice how to run its system. As the mass stored in the heat storage becomes larger and larger, so storage becomes more and more big, then this becomes more and more challenging, let's say, to guess by the user, even though he might be an expert for the site, knowing how the system should be run. He could not grasp all different ways of operation, how the demand occurring 24 hours ahead could be optimally served in terms of the cost of the system running. So what would have to be provided by the user to parameterize this general model? So something that should be available to the user and not too complicated. First of all, the size of the storage. How much, usually water. I suppose that these storages are always with water. How much water you have in the storage. For instance, for whites, it's 38 cubic meters of water, so 38 tons would be this mass. Then next parameter that should be provided, or even advised to the user if he doesn't know exactly what it would be. So this is the power dissipated from the storage per 1 Kelvin of temperature difference between the inside of the storage and the outside, and it's usually in the range of several watts per Kelvin. So if this is even not known, but usually this data is available for the storage and provided by the designer of the storage, because he or she actually used a certain amount of insulation material and certain let's say thickness of the steel for the storage, and finally this data could be known from it, and the designer of the storage should be aware of these losses the storage has towards the environment. Then next thing that should be provided is the time for heat up of the heat source. For instance, what we saw for whites, once the boiler is engaged, that it takes some maybe 15 minutes time for it to finally fully develop its required power and supply the storage. So this is this heat up time, and also with the same dynamics, we model the cooling down of the heat source once the heat source is switched off. And then parameters A and B are actually this linear interpolation of efficiency of the heat source for different loading conditions of this heat source. This is usually provided maybe like 2 dots. One efficiency for a partial loading, one efficiency for full loading, and then simply from these 2 dots you can pull or you can create a line, and these A and B are actually parameters of this line. Okay, and this would be the whole parametric setup. So these parameters are the ones that user should provide. So I don't think that either of them is too much problematic, let's say. So this is something that a user could give. And this is something that should be then provided through Excel at the end, when we will have the module in Excel. What additionally needs to be provided to give a very concrete advice to the user how to run its system, when to switch on its sources, when to switch them off, with how much power then they should be engaged when switched on. The additional things we need to provide from the user side is actually the scenario in which our system will be used. And this scenario is consisted of heating demand, so power that needs to provide, heating power that needs to be provided from the storage towards the consumers. And we can discuss, of course, how the user could know it. But for instance, this could be an information available on calorimeters if the user can see that it has like repeating heating demand from day to day, or let's say similar patterns for different working days in the week, similar patterns for different days of the weekend, etc. Then he would be finally in a position to guess the heat demand 1 day ahead, and this guess for the heat demand would be required for us to advise him how to run this system. So this advice is given here as this P demand. It would be like a collection of points in time, showing how the demand evolves through 24 hours ahead. We can make it, of course, more detailed or more coarse from the user side. So a user can actually set some number of points in which he would guess the heat demand, and then the rest would be actually interpolated at the end. But in general, it would be possible to give the heat demand profile up to the level of 15 minutes sampling time. That is the time I didn't mention so far. So this would be the time granularity with which we could provide in the most, let's say, detailed way the advices, but we figured out that these advices for 15 minutes by 15 minutes time intervals would be too complicated to follow and to maybe schedule and program for the local automation. And that's why, of course, we can make it more seldom in time, such that, for instance, for 3 hours we may keep the same power of the heat source. That's also viable, and these are the ways we have computed the results so far. So you will see, to make it more user-friendly, more easy to program. But considering a more advanced case, when you would trust this tool and you would have actually a computer on your site interfaced with it, then it wouldn't be a problem even to follow it on 15 minutes time frame with a computer who is in charge for this. The other parameter needed to provide to explain the environment, the scenario for the tool would be this environmental temperature. So the temperature in which you have your environment around the heat storage, because this is what is needed for us to model these losses. Sometimes it's really easy to guess when it's somewhere inside this heat storage, then it's usually a temperature around, I don't know, 20, 21, 22 degrees, where the storage is located. Or maybe if there are some heat leaks in the central heating station, then this temperature might be even much higher. But eventually, it's more or less easy to guess it, how it will be. And if, for instance, the storage is placed somewhere outside, this is the case also for white. So part of this storage is if I recall, interfacing the environment, because it's too big to fit in the existing building. So in this case, you would need to know also the environment temperature. So this would be like data from the weather forecast, for instance, for the day ahead. And you can provide it also as a time profile, or if it's not very dynamic, for instance, for the case when the storage is situated somewhere inside, then it would be just one number for the whole 24 hours. So parameters needed to be provided by the user, and definition of the scenario. But of course, there is something else to be provided, namely different sources have actually available different minimum and maximal powers when they are switched on. So it's not that when they are switched on that they can be run with any power from 0 to maximum, but there is most usually, at least from the things we encountered on all our pilots, a situation that you have a minimum power with which you can run your system, and you can run your source, and this power can be finally raised to the maximum available power of this heat source. And of course, the source can be switched off. That's why we need to know this minimum available power for the heat source when it is switched on. We need to know maximum, so nominal power of the heat source. And actually, we know that the heat source can be found on any of these powers, but also can be switched off. And such, I promise not to burden you with too much mathematics, but this kind of a constraint, which is like a disconnected domain for the power, makes a lot of problems in optimization and in computation. We deal with it, but it's making the optimizations harder. Okay, and now coming back to actually what temperature we want to have achieved in the heat storage. So with which temperature we want to supply our consumers. And usually there is some minimum temperature on top of the storage that you need to have always achieved, because then you can have a normal heat supply to your consumers. And since we are in this simplified model, modeling our storage as storage with one temperature, let's say mean temperature, actually representing the overall power that is contained in this storage, so equivalent to the overall energy contained in the storage. So we need to somehow install a constraint for the temperature at the top of the storage. And to make this thing simplified, we can make it, of course, complex. We can model the storage in layers, and you will see how this is done for all three sites. I will show for Bračak, and also Philip and Philip R and Philip V will show it for Vajec and Lendava, respectively. And here, for this simplified model, to make things easy to handle, fast to compute, etc., we would require one additional data from the user, and this would be actually the temperature difference, usual temperature difference that occurs in this heat storage from the bottom to the top. This is something that is available usually from the SCADA system, and there where you have several sensors along the vertical profile of your storage placed, then you are able to measure all these temperatures along the storage, and you are actually in a position to know how different this how big is this stratification, and how different are the temperatures from the bottom of the storage and from the top of the storage. And this is the delta T provided here. So we are considering that we model with this one equivalent temperature some middle temperature in the storage, and then half of this delta T summed with this equivalent single temperature of the storage would be our approximation of the top of the storage temperature. And this we want to constrain. So the user can set, I don't want this temperature to fall, for instance, below 60 degrees, and I don't want it to rise above, I don't know, let's say 90 degrees. And so what would have to be provided by the user from the things mentioned on this slide are, once again, to repeat, minimum available power when heat source is on. So the heat source cannot run with lower power than P min. Then it's nominal power, P max. And then the required, so this is like a user requirement, required interval for the temperature on the top of the storage. So the one that is being supplied to the consumers. This is T min and T max. So this one is not something that user should know from the system, but actually should pose as his or her requirement. And finally, what would have to be provided to help us with this simplified modeling of the storage is the temperature difference, usual temperature difference incurred in the storage when operating from its bottom to its top. So the temperature of the highest level of the storage subtracted from the temperature of the lowest level of the storage. This would be this delta T. This would help us then to pose the constraint regarding the top temperature of the storage while using this mean temperature T. Yeah, and I figured just one thing in this equations I have given to you now, if somebody maybe has noticed. So this temperature here in this equation is so middle, let's say, representative equivalent temperature in the storage. This letter T here is a time constant of the heat source, so I should have used a different letter here for the for this time constant. Maybe add something here down, maybe THS or something like this. So this T here is not temperature. Sorry for that. This is also here the same thing. So T, let's say we can put HS, and THS would be like a parameter needed. Okay, so having said all this, now let's see how it would work on an example for whites. The parameters and constraints the user would need to enter. Mass of the storage, mass of the water in the storage, 38 tons. Then this is a parameter that would just need to change if we wouldn't have the heating medium being water. If it's water, then it's there is no need to provide this C. We know it, but if it's maybe some other medium, then this C could be selected and changed. If it is water, no need to provide anything here. We know this parameter, so this is specific heat capacity of water. How much energy you need to provide to a kilogram of water to be heated up by 1 degree Celsius or 1 Kelvin. Then this is the constant for losses of the storage. For whites, we have it as 3.3 watts per Kelvin, or having here everything entered in kilowatts, this is 0.0033 kilowatts per Kelvin. Then efficiency. What we found from data sheets of for whites heat sources, so wood pellet boilers, no, biomass boilers, sorry. I'm not sure whether there are wood pellets, but biomass boilers. We have like 2 points. Efficiency for partial load, which is actually 0.92, and efficiency for full load, which is 0.9. So this is something that is a bit different from what we have in different preparatory document for the pilot, where we argued that the heat source should be run on its maximum power in order to operate with maximum efficiency. So actually, from the data sheets, it seems that the boilers are more efficient on partial load than on the full load. However, and these efficiencies do not differ very much. And you will see what consequence it has on the optimization and the devices. To better demonstrate what the tool can do, I also intentionally used one more setup for efficiency, a setup for in which in partial load you would have 0.7 efficiency. For instance, when the power of the heat source would be half of the maximum, then you would have here 0.5 times 1/2 0.4. This is 0.7. And when you would have like full power, this would be 0.5 plus 0.4, that's 0.9. So efficiency 0.7 for partial load and efficiency 0.9 for full load. It is like another setup I would like to show you, just to see that in one case there is a reason to ask for advice, and in another case, when you have such small differences in efficiencies, then it may be that you cannot profit from the advices provided, and that the simple automation system would be quite enough. Then the constraints for the for whites, and here to explain this equivalent source. So actually in whites there are two boilers. And you will see the setup more in details. Philip will provide it later on. One boiler of some 250 kilowatt nominal power, and another of some 500 kilowatt. So overall, it's 750 summed up. I don't think I guessed the numbers correctly. Maybe the smaller one is a bit higher power, and the larger one a bit smaller, but the sum of nominal power is 750 kilowatts. And the minimum power of the smaller heat source is 80 kilowatt, and that is then our constraint. So minimum power we can engage from our heat sources is 80 kilowatt, and the maximum power is 750 kilowatt. Then next, what we have, for instance, seen from the responses recorded on white site is that usually this stratification of the temperatures in the storage at the end gives some 15 degrees overall temperature difference from the top to the bottom. And this is something that we entered also as a parameter here. This should be provided by the user, because we want to actually model in this way, in this simplified way, the stratification in the storage, such that we can pose the constraint for the top storage level. And for the top, for the place from which the water is supplied to consumers, we are giving minimum and maximum temperature constraint as users, as our demand to this module. So the things you see here are parameters and constraints for this setup for whites. So things that should be provided to the module in order for the module to perform the calculations. And of course, we need to provide the scenario. For whites, the scenario we considered is a constant environment temperature of 10 degrees. And regarding the heat demand profile, it is the one shown here. So you can see the range of heating demands occurring on white site. This is recorded on calorimeters on the site. So it actually resembles how the demand behaves during a particular day. So once again, to repeat, for the module to be effective for the user to give a useful advice, this demand should be predicted and provided for day ahead. But there is also another scenario to be considered for usage of the module, where you can analyze how efficient your local automation is, and you can decide post festum whether it should have operated differently, such that you actually engage the demand to this module as recorded on the calorimeter for a particular day, and see for this day how your automation system was running and what was the optimal advising for running the system for that day. And you can then even see whether you need to change something on your timers in your simple automation system regarding on and off times of your heat source to gain on the system operation efficiency. So it's not that it is only possible to be used for day ahead advising, but it can be also used to analyze the operation of your site and to see at the end, are you operating your heat sources efficiently or not? Is there a place for improvement? So now come actually the calculations. One, we have entered the parameters, constraints for this heating system and the scenario for its usage. Now come the results. So the results I am providing you here are the following. The blue line given here would be the main output from this module, telling us how we should run our heat sources, with how much power they should be engaged over time in order to be as efficient as possible. In this case, for whites, we wanted to minimize the primary energy used, so the biomass needed to be used to actually run the boilers. And since these advices are provided to the user, they are given as blocks. So this is 24 hours ahead period, you see. So this is some 86,000 seconds. Time is in seconds, so this is a full day operation, 1 day ahead. And I will explain what the red line is. So the blue line gives you advices how you should run your system in blocks of, so these are 8 different blocks. So these are blocks of 3 hours, 24 hours through 8. These are blocks of 3 hours. So each 3 hours, like a constant power reference for your heat source. The situation here, which I wanted to stress, is the situation where the efficiency of the heat source is better at full load than at partial load, meaning then that the system tries to have a focused operation of heat sources at one part of the day, and then really a small, let's say, amount of power in other parts. In this way, trying to use this more efficient way of the boiler operation. And also, what we are using are the residual heat, which is available in the boiler once it is switched off. So we are also using it and taking care of it with the model, because we consider that still there is available power in our heat source once we switch it off, because you have this source and its, let's say, metal mass is heated up, which still can provide heat to the water running through it for a while. So, for instance, for whites, this is some 15 minutes time. And this is how then we have also tuned our time constant for the heat source to resemble this 15 minutes ability to provide heat even after the heat source is switched off. This is, for instance, not considered in a simple automation, meaning that when it switches off the boiler, it doesn't take into account that still there is a remainder of heat in it, and if the heat is not needed, then it's just wasted on in your storage at the end, because you heat up water to a higher temperature, which at the end is not needed. Okay, and now what the red line is. We wanted to provide a certain comparison, because it's always good to see how this optimal advice would perform in comparison to a simple automation. So, for instance, a simple automation that just tries to keep the temperature on the top level of the storage at a certain level, for instance, ensuring through engaging of heat sources that on top of the storage you always have 80 degrees. And this is how this automation would run throughout the day. This is how it would engage the heating powers in your heat sources. This is this red line. So it always follows the current demand. So it tries that the power of heat sources corresponds to what is currently being required, and then additionally changed with respect to the current temperature in the storage. If it is too high, then the power is diminished from, decreased from the current value of power demand. And if the temperature on the top of the storage is smaller than what is required, then it gives additional power to what is required from the current demand. And that is how it always manages to keep the temperature at the right level on the top of the storage. So this is like a simple reactive controls, and we wanted to compare it, how it performs with respect to these advices. So in a completely same setup for the same model. Before I show you that, so the performance, here it's just shown how the temperature, this equivalent temperature in the storage changes for the case of this optimized operation. And this is the blue line. You see that you have several, let's say, trips to higher temperatures in the storage. And considering that we have 15 degrees temperature difference from top to bottom, and considering that this is actually that T is a mean temperature in the storage, then you would have to add 7.5 degrees to this middle temperature. And that's how, for instance, with this red line, when we regulate with simple automation, you have 72.5 degrees plus 7.5, bringing you to 80 degrees on the top of the storage with the simple automation. And here, since we allowed that the temperature of the storage can be risen even to 90 degrees, we have then these trips to even 90 degrees here. And this is, of course, viable and okay if you have very good isolation of the storage. In this way, you can more focusedly engage your heat source if it is more efficient on a higher load, as it is provided here. And in this way, you get on the overall efficiency. But for instance, if your storage has higher losses, then probably this won't be very well accepted, and you would actually you would not get this as a benefit. But of course, the optimization outweighs these two. It takes care how much you are losing through the connection of the storage with the environment, through the isolation of the storage, and how much you get in efficiency if you run the heat sources at full load, for instance. Okay, and now just to see for the two different scenarios with efficiency, what we get currently as a result of optimization. So we are not still completely satisfied with how the optimization is run, and consider that these two numbers at the end will be even lower, because we see from the results that still the optimization procedure can give better results. There is a space for improvement, but this is what we currently have, and this is what I'm showing you. So this is computed in MATLAB, where currently the whole module is implemented for this simple model. And what you may see are the primary energy uses, daily primary energy uses. For again, for the example of whites and this particular demand profile I was showing you before. And the green case is actually not the case for the site, because the data sheet says that we have 0.92 efficiency for the boilers on partial load and 0.9 efficiency on the full load. And even though you may see that these efficiencies are quite similar, in that case, some advanced planning won't give you much benefit. Basically, you don't get benefit from just engaging more your heat source from and tripping with temperature on higher values for a while, because simply you don't run on higher efficiency. And in that case, it's good enough to just have a simple automation and fully rely on it and keep the temperature all the time on 80 degrees, or maybe if some other reference temperature is required, the automation can give you the correct amount of power to achieve it. And even you may see that for this case, the optimization result is even worse than the simple automation. In terms of kilowatt hours engaged. Since these efficiencies here are higher, then you may see that of course, the primary energy uses on the biomass side are lower. And for the case when you have significantly varying efficiency, and where the heat source is more efficient on full load and less efficient on partial load, you can see benefits coming out of this optimized devices. So even though we have just a reduced number of moves, just 8 moves during the day, compared to the simple automation which can change the power anytime, we are able to get better results, and they can even be further improved. Sorry, my scroller took me away. Okay, so these are the results from this simple module applied for whites. Philip will show you whites in more details with this more complex model. So are there maybe some questions here regarding this suggestion, how we should, or comments or whatever, how we should use this simplified model for the heating system, which could be then provided to a general set of stakeholders, something that can be given as Excel on the web, downloadable tool, and then run by different stakeholders, and finally us being useful for the Central Europe through this project. So what do you think about of the module? Comments, questions? I hope I didn't kill you, and I hope you understood what.
Mario,
yeah.
A very short question. I'm not so technical, but when you talk about environmental temperature, you said 10 degrees. This is the environmental temperature required at the user on the user side. So because it seems low.
Yeah. Okay. So this temperature is actually the temperature of the surroundings of the storage. Okay. So for instance, in case of whites, the storage is partly placed outside the building. So actually on the outside temperature. And this is the temperature we have then used. Part of the storage is inside in the building, and part is sticking out, if I recall well. So this is something like then a mean between the temperature that is inside this room where the storage is located, and between the environment, because part of the storage is sticking out. And that's why I have put. So it's not the temperature of the spaces which are heated from this heating system. Of course, no room is comfortable at 10 degrees. So this is a temperature of the surroundings where the storage is located.
Okay, thank you.
Just to comment that we did not fall asleep, and so far everything is clear as far as I'm
Great.
concerned.
Okay. Okay. Thanks, Minik. Okay. So I would continue now
Mario,
with
just one question.
yes. Okay,
How
Wolfgang.
do you know the temperature outside in advance if the storage is put like in whites in the open? Is it connected somehow with a postal code, or how does it know where it is?
Yeah. For now, it should be manually provided by the user of the module. He should, for instance, if it's completely outside, he should take a look at the weather forecast and give us this information.
A manual.
Yeah, of course. So we wouldn't be the ones who would be connecting to the weather forecasting service to get this out. For now, no. So it's something that the user should provide. Yeah, but this is, I think, the one of the easiest data to be provided. Yeah. So it's and even it can be given as a profile. So it's not a problem that, for instance, if the user knows the profile, if the storage is outside, and there is a temperature profile that changes throughout the day, it can be also entered. So no problem to handle like temperatures that change with each 15 minutes. So it can be more detailed, but at the end, it can be like some middle temperature. Usually when it's inside, it's about 20 degrees. So it's not that problematic to enter. And the lower the losses are, so this coefficient for losses, if they are lower, then this actually data of the temperature, it becomes less and less relevant and doesn't influence much the results. Yeah. So I don't know, I wanted to ask you additionally, what do you think about this advising form with these several blocks of constant powers that are advised how the system should be run? Is it something you see as acceptable to stakeholders and users, either for analysis or even to set up its local automation when the sources should be switched on, when switched off, etc.
I was reminded to portfolio management of, let's say, bigger energy plants.
Mm-hmm.
It is something like that.
Yeah, it could. Yes. So it's, let's say, Michael, it's all set up to be used in fully automated scenario. So you could actually supply all the data to the computer each 15 minutes, and you would get the optimized profile for the next day. So it would be like supplying the computer with what needs to be done with the system. But we are not in that position on either of our sites, and that's why we have chosen this offline direction, because the best we can do is to provide the software which can then be used for checking whether the local automation does things correctly, and for maybe tuning it up and setting certain timers for switching on and off of different heating sources by help of this tool. Or maybe if you have a keen operator, you can even have him following these advices 3 hours by 3 hours, or maybe we can make it more coarse, I don't know, 6 hours by 6 hours to make it more easy for the user to apply. But yes, indeed, this is like planning that would be done in the same way if we would be doing it online and talking to a computer that always needs to set up every 15 minutes the plan for the coming period, and this this beginning of the plan, it would actually implement on the equipment. Did I answer, Michael, what you asked?
Yes, indeed. I mean, you would like to do it then online via an Excel sheet, right? That's what you have mentioned.
In usage, yes, but I wouldn't use the term online because it's something that is computed based on the data entered manually by the user. So he would have to provide us this demand profile. It wouldn't have to be that detailed. It could be like a small number of points which are then connected in between, interpolated. But this needs to be provided by the user, and the environment temperature. With these two things, of course, considering that user has parameterized the module and entered all these parameters here, then he can use the module for different situations that occur on the site, and he can be advised how to run its heating system. But it's not online, so it's just computing advices for some time ahead, let's say. You, for instance, computed a day before for the next day, and then set up your timers based on it for turning on and off your heat sources.
Maybe if I can add just a bit to this.
Mm-hmm.
So far here and now at our location, our system that manages the heating system has practically only two parameters, more or less. So basically, I'm either in a heating mode when the building is occupied and a bit before, or I'm in a standby mode when there is nobody here, and it is used throughout the night and throughout the weekends. In this way, if we calculate it, maybe we could change those scenarios for the system and improve this efficiency. That would be, I would say, that would be the biggest benefit for us.
Yeah. So Miljenko, if there are like two regimes with probably different required temperatures on the top of the storage, in that case, these minima and the maxima can be changed over time, and this can be taken care of by the module. And of course, we can do it in a more, let's say, simple way, and ask the user even if it can provide only one temperature, and if he would like to provide profile for minimum and maximum, he would be able to do it also. And in that way, he would be getting, let's say, realistic advices how to run the system. But so this can be entered as a profile throughout the time, so for each 15 minutes, and no problem. Or you can put it as blocks of time, so no problem in any case. Okay.
I have a question actually.
Mm-hmm.
What happens if someone forgot to input the temperature for the next day? Does it automatically take the temperature of the day before, or is there an option where they can add like the temperature for a couple of days ahead?
Mm-hmm. So this is for advising the user how to run the system. Basically, you have always the local automation there. It's not that you would rely on these computations here, and that you would have to run them in order for the heating system to run. It would be like just to improve and tune your automation system, but it's always there. And for instance, if your temperature drops because the demand is higher than you expected it to be, the local automation will react anyway, and will cover it up. So if the scenario is different, the local automation will do its job, And finally, this is just for, let's say, local, in advance tuning some parameters of this automation system, maybe certain timers. But at the end, you are always, with local automation, regulating the temperature on the top of the storage in order to keep the water prepared for the user. So it's not that you would rely on this module. It's offline, giving advices how to improve the system, how to make it more efficient. But it's not that everything would stop if somebody would not be using it. So it's always like local automation there.
Okay, great.
Yeah,
Thank you.
yeah. If you would have online execution of this code, I was mentioning it. It's a possibility with a very advanced system where you have a server available locally that is connected to your SCADA system, and then this server computes exactly these power profiles and engages the system with these profiles. So the beginning of the profile, it directly commands to the system, and the rest is its plan. And this plan is always repeated, for instance, each 15 minutes. In that case, you have a computer running online, and that is completely different. Then you rely actually on this system, and you replace what was local automation before, or local automation is just a support that things are being corrected if something sudden and unpredicted happens. In this offline setup we have now, because we have chosen not to install any IT support on either of the pilots, so we have traced this path already at the very beginning of the project in order for the tool to be as useful as possible. So this is the scenario we considered, and actually the most relaxing for us, because nobody is going to blame us for anything. There is a simple automation local is still available, and we are just providing the advices if it can get any better. But so every day minute-to-minute operation is on the side of the local automation. Okay. So maybe some also other questions or comments regarding this procedure. So at the end, the user interface, which I cannot show you because we don't have it, all the computations were for now done in MATLAB, with algorithms in MATLAB. The user interface at the end will be Excel table. We excelled in Excel, let's say. So with module 1 and a similar thing we will also apply then here. So it will be then I think a nice a piece of software at the end available for the usage, for advising whether a certain plant can get any better from the way it currently is being run. Okay. And all these parameters here would be entered through Excel interface. And we can put, for instance, what Miljenko was asking about these temperature profiles, we can put them to change over time, required minimum maximum temperatures. Even this can be used to perform some very special operations like Legionella protection, where, for instance, once a week you need to put higher temperatures in your boiler for a particular short amount of time, maybe 15 minutes, half an hour, I don't know what is the exact recommended procedure. And then you could also see how to achieve this in an efficient way by setting for a while these temperatures on higher values compared to what you usually need to have in your system. Okay, so this would be entered by Excel. If this advanced way of entering minimum and maximum would be required, then this can be entered as profiles. Similarly as also demand. So as you know, we also can have for module 1 these custom profiles, and the user can supply, for instance, for module 1 the profile of the consumption of each site throughout the year. So here would be a profile of consumption throughout the day, which would be coded as a set of points and times. So it doesn't have to be detailed like this. This is recorded on a calorimeter in bytes each 15 minutes. But for instance, can be with a smaller number of points, which are then interpolated. But it can be provided as this profile. Okay, so what I else wanted to show you before I give floor to our Philips. Let me see the time. Oh yeah, I said maybe we will be short, but okay. I thought we are comfortable with time, so I'm not speeding up too much, and I hope it's comfortable also for you to follow, and it's okay. When it becomes fast and hectic, then we lose each other. Okay, then let's focus a bit now on Bračak. I wanted also to explain the results we have for Bračak by now. Viljenko will, I hope, will pay more attention. These are still not final results, as we need to still work on the optimization procedure. But actually, the results are already here, so we can see how they look like. So what happens when actually you have a real heating system in front of you, and you want to model it in more detail? So not to have like a simple storage with only one representative temperature, but actually a storage in layers where you model stratification, and you have then, for instance, here for the case of Bračak, the storage with 5 different layers. They have been chosen with respect to the temperatures and levels which are used for different heating sources. Either they are supplied on these levels, the temperatures are supplied on these levels from heating sources, or the water for the heat sources is sourced from the storage on particular levels, and that's how we finally decided to have these 5 levels. But let's see what is connected to this storage in Bračak as heat sources. We have actually 2 heat sources. One is CHP, so combined heat and power, which needs to be really carefully planned when used, because it has some constraints regarding the maximum temperatures it can receive on its input from the storage. And in order to keep it engaged, and we will see it's very lucrative to have it engaged, to keep it engaged all the time, we need to obey this constraint. What should be the temperature at this particular level in the storage where the water is sourced from for the CHP? If this temperature is overstepped, then CHP can no longer operate, cannot provide the heat, and this is bad from the point of view of economy of the plant at the end. We have also another source. It is a wood pellets boiler, which also takes water from one level of the storage. This is this level 3. Takes the water, heats it up, and returns it to level 2. You can see this circle for the wood pellets boiler here in this graph on the left. So this one, I'm going through it again. And the other one is for the CHP. You see that CHP is taking the water from lower locations to be able to have this more cold water that is required for its operation, then heats it up and returns it back to the same level where also wood pellets boiler returns the water. And we have consumers then connected to this storage. In this more detailed setup, we require more data also for the heat supply to the users. Namely, we require both the heat demand and the flow of the water that is engaged. And actually, I won't be, let's say, too much saying you how difficult it was to model it. But basically, when you have these flows going in and out, you might have different directions of water flowing inside the storage, and this complicates the model significantly. And you need to take it into account. It very much then determines how the heat is exchanged within the storage. So it's definitely a much more complex model than the one I explained you before. With this simple approach with one equivalent storage. And in this case, there are different scenarios in which you can have the water flowing just inside the storage and being exchanged between different levels in the tank. So towards the user, the water is sourced from the top, here a temperature T1, and the water is returned. So cool down water from the users is returned through this bottom of the storage, and it enters layer 5. And now just going directly to the scenario we used for the Bračak site. So this is the load we assumed for the Bračak site. You see it is power in kilowatts, so heating power in kilowatts, and you see how it behaves throughout the day. It has a peak in the morning and peak in the evening, and just one additional small peak in the middle of the day. Of course, this is not probably a full winter day, but you have like some partial heating load on your system. So when people come to work, they heat up their spaces. Then some peak during the day, probably I don't know with what is it connected. And in the evening, when it becomes more cold, then you have this again more intensive usage. And finally, when everybody leaves the building, then the usage again drops. And besides this heat demand profile, we have also the flow of the medium coming out from the storage towards the users, and this resembles, let's say, these 3 peaks that exist. So you can see how this looks like. We have 3 periods when the flow is at about 1 kilogram per second, and in other periods the flow is 0. Okay, so these are the data needed for the scenario. Once you have a parameterized model, this more complex one with several layers in the storage, and then we can see what we have as results. For instance, when you have a simple automation which cannot ensure that there is always proper temperature in layer 4 for the CHP to run, you can just think of using, for instance, wood pellets boiler. And I can enlarge it. Sorry, I will enlarge it such that you see better. Okay, not to move the figure, just to give you more the idea from what we started. Okay, so like initial guess for the operation of the system when only wood pellets boiler would be used is this yellow line. Power from the CHP is always 0 here, which is bad. And the demand is the blue line. Okay, so demand is from the preview figure, and this is how the temperatures in different layers behave for such operation. So you have temperatures in layers T1, T2, T3, T4, T5 with different colors provided. And you can see how this operation of only wood pellets boiler would resemble in the behavior of temperatures in different levels of the storage. And the blue line T1 is the one that is actually temperature that is being supplied to the end users. And with such operation, the daily cost for here just the pellets, which are then used for running the wood pellets boiler, would be 14.75 euro. Okay. And in the other case, I'll zoom out. After you perform the optimization and get the advices, this would be the profile. I cannot say that this is the final result we would have for this scenario. Sorry, I won't be into getting into the presentation mode. Rather, I will enlarge it also here so that you better see. Oh, it doesn't listen to me. Okay. So you will see now that you are always trying to engage CHP in this optimized profile for as long as needed, and you reduce the usage of wood pellets boiler. But this can be done only so if the temperature level T4, this purple one, is kept below certain level. I think this level is 64 or 65 degrees. I'm not sure what is the, but this number rings in my head.
It's 65.
65. Okay.
Yeah.
So whenever the temperature in layer T4 rises above 65 degrees, you can no longer use CHP. And you see that you strive with your optimization to run the system in a way that whenever the heat is needed, that you engage the CHP and you have your temperature in layer 4 reduced and on a proper level that enables your CHP to run. And that in this period, I don't know, from let's say 12 to 16, because of the temperature being, because the water is not used, the temperature has risen and has equalized with the highest temperatures in the tank, then you cannot use CHP. And for instance, when the load here rises again at 16, you first wait for the things to get a bit cooled down in the level 4, and then you again plan to engage your CHP. And what you get with this careful execution and running of the system is significantly reduced cost. So if you would use only wood pellets boiler, this is some 15 euro, let's say, roughly, and this here is some 7 euro. So it's almost like cut in half the cost. Why is that so? Because when CHP is used, actually it produces also electricity, and we take into account that with this electricity produced, we reduce the electricity consumption of the object, and this is where the gain comes. Okay, because the price of gas, which is used to run the CHP, compared to the price of electricity we are actually avoiding with producing electricity locally, match good. For at least this was for the scenario we considered, but this is, I suppose, how economically these prices are posed now. And you get this practically, let's say, the heat you are getting for free, almost for free, because what you are using in gas, you are supplying in electricity, and the money spent for gas is compensated with practically with reduced money for electricity, and then the heat is like coming. Okay, it's maybe easy just to say for free, but it's probably of very low cost compared to the case when you use it from the wood pellets.
Just one sentence. So yes, you are right here, and the difference between the price of the gas and the price of the electricity, it is important to take into account the time throughout the day, because we have a different price in the morning for the electricity, yes, and different in the evening. So in the morning, it is much more beneficial to run the CHP, and in the afternoon, not really so much.
Yeah. Okay. Yes, Milenko, you are correct. Well, Philip will know better. Philip, did we take into account the tariffing of electricity here?
Yes, we did. So during the night, the price of the running CHP is positive, so because the price of the electricity is lower. So that's why at the beginning of the day, while it's still the night, you see the temperatures are still around 60, which is the low. While during the day, when the electricity goes, electricity
you
price,
refer to this figure, right?
Yes,
okay,
that's right. So in the day, when the electricity price goes up, the cost for running the CHP becomes negative. It's just somewhat negative. So you actually, let's say, gain money, but you don't, because you don't sell the electricity, you use it in the building.
Yeah.
But
like watching for the heating system just for the heating system and neglecting electricity, it's like heating system selling something to the electricity and gaining money from it, right? Something like this.
Something like this. Yeah.
Yeah. Okay. So in this case, you may see that a careful planning and this more complex model adapted for this site would give you this benefit. And I said in the beginning, so Lendava and Bračak are more exotic heating systems, let's say. Whites is more classic. And for these cases, for instance, still in, let's say in Bračak, maybe this simplified procedure could be used, could be of interest, but definitely not just by providing this simple version we are going to give publicly. We would have to have at least some adaptations to take into account the specifics of CHP and the wood pellets boiler. So we wouldn't have just one equivalent heat source, because it would be wrong. The problem is in details here. Let's say that really this heating source cannot be represented as one equivalent, because they are so different, and it's all about when which is run regarding this benefit you see here. So this simple model would require some adaptation, some let's say enlargements, even without modeling stratifications, etc. But just this, that at certain level in the tank, we would have to have certain temperatures. So if we would model the tank with the mean temperature and with knowing this temperature difference from bottom to top, we could roughly say what would be the temperature in layer in layer T4, which would then enable us to run the CHP. But it's really specific, so it's I would say an exotic type of a heating system for which you need then more dedication. Yeah. And similar it will be also with Lendava, yeah, because of the special type of the storage, and you cannot actually. There is the problem with C, the coefficient of the heating parameter. The heat capacity, sorry. So at the end, this C in case of Lendava changes with temperature, and there is a span of temperatures where this C is extra large since we are using the latent heat from the paraffin, and this would then require even in this simple version without considering stratifications of the storage, certain adaptation of this simple model. Yeah. Okay. Yes, so that's what I wanted to show about Bračak site and to comment these results a bit. And are there maybe some additional comments or questions regarding this?
Maybe just a bit from my side. We see that here we can achieve quite a lot with this kind of system. And of course, when we add to that the photovoltaics which are in the progress, I think that the model will get quite a bit more complicated than this.
Yeah, but we are just considering here the heating system. Actually, okay. Yeah, together with batteries. Yes, you are right. Yeah. So if you would model also the let's say microgrid level, which takes into account also electricity flows. Now, when we have batteries and the photovoltaic system, then it is very interesting and challenging to control overall. But for instance, the heating system can be optimized on its own, let's say, and batteries and photovoltaics. Let's say batteries, photovoltaics are producing maximum. So batteries also on their own, and then let's say that can be somehow simply interfaced with each other. But yeah, that's a very nice example how actually these optimal controls and efforts in modeling the system and finally computing this optimal controls when it makes perfect sense at the end. Yeah, and it gives revenues. So the more and more complex systems get, then there is more and more space for something, let's say, like this, that is very careful with different sources that are engaged. And yes, it's very interesting.